Okay, so before we're going to start the seminar, just we need to establish a little bit of a procedure. It's our first time that we actually have everything online. And one thing that we would kindly ask once the speaker starts, if you would kindly turn off your video feed just to preserve any bandwidth, and please also mute your microphones. Another question that we have, if there are another request on our end, if there are any answers, please keep them towards the end of the presentation. And there is a symbol called raise hand. If you open up the list of participants, it should be on the very bottom of it. And if you would be so kind and just raise your hand to indicate that you want to ask a question, and then I will go through the list and try to funnel you towards Dr. Omer in this particular case. Another thing, if you want to convey any emotions, it's a little bit difficult, but if you go to the very right, there is a button that says more, and there you have, for example, the clapping the hand symbol or the thumbs up, right? Well, welcome everybody to our very first seminar. It has been quite some time, and it's great that we can sort of at least convene again. And I want to introduce our speaker first. Does he need a lot of introduction? Well, actually not. It's his second time that he is giving a talk, thankfully, for the CIPR seminar. He's one of our very own, Dr. Omer, and just if you don't know already, but he's originally from Pakistan, to be more precise. I think he's Karachi, actually. He got his undergraduate degree there. He then got a degree in Turin, in Italy. His PhD is actually from KAUST, and then he went to a really cool school called Princeton to get his postdoc, and luckily he decided to join CPG. He's an expert when it comes to signal processing in the geophysical domain, in particular also the addition of machine learning. And he and Dr. Sharif, for the students among you, he has a really awesome class that you should really consider to sign up. So without further ado, it's all yours, Dr. Omer.
Thank you very much, Gunter, for a nice introduction. And if you could please confirm that you're able to view my screen well, then I will go ahead. All right. Thanks, everyone, for coming to this talk, this seminar. And yeah, indeed, it's been a while that we had the CIPR seminars. And now I'm very happy to kick off for this new semester, although it's kind of a virtual event now. So this is pretty exciting. My talk today, it has a little bit of a story. So when I was leaving Princeton as a postdoc and coming here at KFUPM, I knew that I wanted to do deep learning and machine learning applied to geophysical problems. And therefore, in the beginning, it took me a while to teach myself, the principles behind machine learning and deep learning to the extent that I could teach them to other students and also conduct research in the domain. Therefore, what you will see today is kind of the journey that I've had over the past few years and the things that I've been involved in terms of research and some of the collaborative projects that we are doing. All right, so let me get started. So it is not very common, or it's not very often that we get to see a revolution unfolding in front of our eyes. And the one that we are witnessing is what is being dubbed as the fourth industrial revolution. Now, the thing that differentiates the fourth industrial revolution from the third is the pace with which technology is progressing. And more importantly, the lines between humans and technology is kind of getting narrower and narrower, and the technology is merging more and more into our lives. If we talk about technologies like face ID recognition, self-driving cars, voice-activated personal digital assistants, and you can have sensors now attached to your body. So these are things that are kind of advancing the frontiers of science and also elevating our quality of life, the way we live in the modern world. And nowadays, in fact, you could have a hip replaced with a 3D printed hip bone, in fact, or you could have a bionic arm nowadays with something that is 3D printed. So that is kind of the technological advancement that we are witnessing in today's world. However, like all technological advancements, what we also see is some skepticism from the public, from some domains of the public. And this is not new, actually. while we are seeing, or while we are reaping the benefits of electrification and how our quality of life has been elevated by the electrification of the society, some of our ancestors were still anxious about electricity being introduced into our society. And during the 1900s, they were having this same conversation that some of us are still having about AI. And I really like this quote by Andrew Ng, where he says, AI is the new electricity. And the reason why he says that is because just like electricity transformed every industry on the face of the earth, AI is going to do the same. So essentially, there is no point resisting. Rather, we should think about how we can adapt better to be prepared for the future that is lying ahead of us. And now just trying to clarify the different terms that you would hear when you see people talking about artificial intelligence. Sometimes people say machine learning, deep learning. So what's the difference between each of these? So primarily today's talk is about deep learning, which is a subset of machine learning in which we use deep artificial neural networks that learn from vast amount of data. And machine learning is kind of a generalized field, a broader field than deep learning, which contains other methods and techniques. And likewise, artificial intelligence is a broader term as well. So specifically, I'll talk about deep learning today. And one question that comes to our mind is, why now? Right? The ideas behind deep learning have been known since the 1980s. So what is it about today that makes it so special with regards to deep learning? So there are essentially two things that I want to highlight here. So one is increase in compute power, and that has been led by modern GPUs that have allowed us to crunch numbers at a much rapid pace than what we could in the olden days. And also the other thing is the amount of data that we have now. So while in the past these older algorithms could outdo deep learning because we were living in this domain where we had very little amount of data available, but nowadays in our digital world we have so much data available that we could train our models on and we could learn from them. So forget about companies like Facebook or Amazon, the amount of data they are collecting. Even small and medium-sized companies, the kind of data they are collecting, they are able to leverage that data to gain performance for products that they have for their customers. So this is the thing that differentiates deep learning, why deep learning is getting so popular these days. So therefore, this leads us to the natural question of what deep learning is and how can I better understand deep learning and what's going on, when you are training a model and stuff. So let's start by looking at this 1980s era neural network. So neural network is the main technology behind deep learning. So I'll try to describe what neural networks do and how they work very briefly. So in a neural network, what we have is something known as the input layer, where we supply our inputs, and we have an output layer where the network supplies to us its output. And in between, we have something called a hidden layer here. And each of these neurons in these different layers are connected in a fashion which is shown here. So each neuron, for example, in the input layer is connected to each neuron in the hidden layer. And each neuron in the hidden layer is connected to each neuron in the output layer. And these connections, and they share some kind of weights between these connections, between these neurons. So the lines that you see here are actually the weights that we talk about. And these weights and the training of neural network refers to the tuning of these weights that we have in the neural network. And once a network is trained, we say that it has been able to get some kind of optimal weights. All right. So kind of drawing a parallel from human learning, how artificial neural network learns. So this is a personal story. So these days, although I'm too old, I'm starting to learn how to eat using chopsticks. The reason why is because we were teaching our 3-year-old daughter to do so, and therefore I thought it's a good opportunity for me to do the same. And in the beginning, I'm not able to do it. It's very difficult. It's a painful process. And the reason why is because there are some connections in my neural circuitry that needs to fire for me to be a pro at, eating with chopsticks. And those connections haven't been strengthened or haven't been reinforced, or what we call the myelination process hasn't happened. So very similar to that, after several iterations, several tries, I'm able to myelinate those neural connections or to strengthen those weights. I can do the same task like an expert, right? So this is true for any task or any skill that we learn, be it swimming, be it driving. So similar things are happening. In the beginning, we are bad, but over time, we are able to train the neural circuitry with those connections that are properly connected for us to do that particular task seamlessly. Similarly, similar thing happens in neural networks. So let's imagine now we are using this neural network and we want it to be trained to differentiate between a cat and a dog. So what are we going to do? The first thing we'll do is we will collect images of dogs and cats to show to the network that, okay, here's how a cat looks like, here's how a dog looks like, but not just one example, several of those. And what we will do is we will feed them at the input layer. So at the input layer, what we are going to do is we are going to have, the image unrolled as a vector and supplied at the input. If you're talking about grayscale images, these will be just pixel values in grayscale. And normally what we do is we initialize our neural networks with random weights. And therefore, it will be multiplied by, and those pixel values will be multiplied with random weights, and they will be evaluated further by the hidden layer, multiplied with further with these random weights, and the output would be some kind of a random output, right? It would be most likely garbage. It would not be a cat or a dog that we want. And then what we would do is we would say, okay, that's not the output I want. I want this output. So this image was a cat. Learn to recognize it as a cat. And therefore we will say, okay, this is your output and here is my output. This is the error. Go back and update your weights based on this error. Therefore the network goes back, updates the weights in this layer and in this layer. And then this is called one epoch or one iteration of it. And therefore we have to do several iterations because there is something like a tug of war mechanism going on between these weights, right? So it takes time for it to stabilize because we have several examples over which we try to train this neural network. So once this network stabilizes or this tug of war mechanism ends and these weights live in harmony, we have a trained neural network that is able to differentiate between cats and dogs. Okay, so this was the 1980s neural network, or what is called the shallow neural network. What is the thing about deep neural networks? Okay, so what differentiates it from shallow networks? So one thing that you could see from the outset is that it has many more hidden layers. Right here, I'm showing 3 hidden layers. So what is the reason for having such different hidden layers? And the reason is that it allows the network to learn different levels of features. So if we are trying to solve a problem in which we are trying to classify, for example, human faces, then we feed that input, and in the beginning layer, in the input layer, we have just pixel values, at each of those locations. And then the next layer, what it does is it takes those pixel values and try to identify edges in the picture. The next layer, what it does is it tries to take those edges and combine them into forming some more complex features that, as you will see here, you could see some eyes and some other kind of features coming out. And then the next layer, what it does is it tries to further, take it to the next level and identify further more features. And you would now clearly see a nose, a mouth, for example. And the output layer, what it does is now it uses those identified features, combines them to forming an image, and therefore it's able to say whether this was, George Washington or Donald Trump, for example. So this is essentially what's going on and what gives the power to these deep neural networks. Now, another way of understanding this is with the analogy of folding a paper compared to the shallow network. So imagine you have a piece of paper, and what you're trying to do is you have several data points marked on the paper. Your task is to differentiate these different data points into different regions. Now, it's always very hard to draw complex lines on the piece of paper, but if you have the ability to fold that paper, that makes life easy. So essentially what deep neural networks do is they allow you this possibility through these different hidden layers, is that the possibility to fold the different, fold this piece of paper into different regions. And therefore that makes life easy for us in, for example, in classification problems. So this is a little bit of introduction about how neural networks and deep neural networks work. Now let's move on to how they're being used in geophysics and what are the effects of this deep learning technology. What are the effects that it's having on geophysics? Now, there are hundreds of papers that are coming out every year, and if you go back to, for example, 2016 or 2017, you would hardly see even abstracts in popular conferences like SEG that use deep learning. There were very few, just a handful of those. And now you will, if you go to these conferences, you will see multiple sessions every day. on using deep learning or machine learning. So therefore, there is a big impact that deep learning is having, and researchers are starting to kind of understand this, and the growth is really exponential. So what you see here is by no means a comprehensive list. These are just a few examples, such as the area of seismic signal processing or earthquake localization, seismic interpretation, where deep learning is having an impact. So what I'm going to do now for the rest of the talk is I'm going to talk about a few different projects that I've been working on, and I'm going to see how, or let's say explain to you how we use deep learning to leverage its potential in solving a particular problem that we are attempting. The first problem that I'm going to talk about is detecting small magnitude earthquakes or induced seismic earthquakes in the area of Groningen, the Netherlands, using convolutional neural networks. I'd like to acknowledge, first of all, our contributors. So this work is mainly led by my graduate student, Ahmed, and we're also helped by Sharif. And there's a lot of technical expertise from Mike Feller from MIT, and we're also getting help from Seismic in kind of comparing with different techniques. All right. So this is our study area, Groningen in the north of Netherlands. This is the largest gas field in Western Europe. It has been in production since the 1980s. And the earthquakes, people started to experience these earthquakes since the 1990s. And gradually over the years, they have increased not only in their frequency, but also in terms of their magnitude. So this became a big social issue in Netherlands, or a political issue, which raised a lot of problems for the population there, because they were afraid, they were getting house damages and stuff, and they were afraid, because of the increase in the amount of these earthquakes and their magnitude. So the Dutch government decided to reduce production from Groningen, and even after reducing production, a large magnitude 3.4 earthquake occurred in January of 2018, and that led to a huge uproar in the community there, and therefore the Dutch government had to decide to close the field. And this will happen, I think, in a few years. So what this tells us is that we have very limited understanding when it comes to the effect of induced seismicity related to the production rate. And therefore, I think in this project, one of the key things that we are trying to go after is to help us understand what is this relationship, because there is a huge cost associated to it, not only for the operators, but to the whole population that's living there in the entire country of Netherlands, because this is a great source of revenue for them. Okay, so the first thing that we would do in such situation is to try to identify those earthquakes, or automatically detect those small magnitude earthquakes. Now, the challenge with identifying small magnitude earthquakes is that, of course, there is some kind of human activity going on the surface, and then you have a sensor here, and around that time there is an earthquake that happens. Because it's a small magnitude earthquake, it's very hard to differentiate from the human activity that's going on, and oftentimes these human activities masquerade as an event. Therefore, what can we do really to alleviate this problem? So we were having this discussion with Mike, and we were just talking about his experience of how he goes about this task of identifying manually, or how he can say that one thing is an event and the other is a noise. So the story is the following: that in Groningen, they have this kind of a sensor network. So you have an accelerometer at the surface, which is very noisy, and then you have velocity sensors at different depths. So Mike was mentioning that the thing that he uses is he looks at the move out, and this move out tells him that whether something is an event or noise, which means something that is coming from below, like probably an event most likely, or noise that is coming from above, right? And that is something that he uses to differentiate event from noise. And therefore we thought it may be a good idea to see if we can teach a convolutional neural network to do that as well. And therefore this is what we did. So what is a convolutional neural network, first of all? So the thing that I showed you in the previous slide is what is called a feed-forward neural network. And don't be intimidated by it. It is kind of an advanced version of a feed-forward neural network. It has some convolutional layers built before a fully connected layer that you saw earlier. And the reason for having these convolutional layers is to also get information on the spatial correlation between different features. And therefore, this is very good for images. And this has shown remarkable performances in image recognition. And just to tell you a bit of history, so there is this ImageNet competition that used to happen every year. I'm not sure if it happens still now or not, but until 2012, the algorithm that used to win this image classification problem were not based on convolutional neural network. They were some kind of conventional techniques. And the reason why CNNs rose to popularity was after this 2012 ImageNet competition, where CNN was able to beat all the competing algorithms, and then its performance just rose exponentially. And then, therefore, nowadays it's the state of the art when it comes to image classification problems. And therefore, this is what we try to do. Just as Mike's eyes would see whether this is a move out going up or a move out going down, can we teach our network to do the same? Okay, so this is what we do with and this is the procedure of doing it. So what we have now in front of you is the training data. So of course, when you're teaching a neural network, you need to supply some training data. Like I mentioned to you in the beginning, cats and dogs, you need to supply images of cats and dogs first. And the data that we have is from October 2017 to February 2018. So this is 5-month period, which contains that January 8 earthquake, because we are interested in understanding what was happening in the region during this period. And for our training data, we take all available stations in the G network. So that the things that you see here in triangles, green and red, are the stations in the G network. And so KNMI, or the Meteorological Institute of the Netherlands, they identify these events by themselves. So they had identified 47 events. I'm not sure about the algorithm they use, but they use some kind of conventional algorithm most likely to detect these events. And during this 5-month period, they had 47 events identified. And therefore, we take that data from them that, okay, these are events identified, and and we go through each seismogram and see whether we have an event there or a noise. So sometimes you will have a noisy station, for example, so we don't want to confuse our network by feeding the noisy station. So we do this careful process of selecting good data out of bad data. And once we have done that, we go and train the network, and we tell the network, when you see something like this is an event. When you see the opposite move out, this is noise. Or when you see some garbage, this is also noise. Sorry. So then what we do is we test our network on 2 months of data from December to January. And what we do is, because we are interested in this area, which is the area of Zeerijp in Groningen, where this 3.4 magnitude event occurred, we take only 5 stations that are closest to this large event. And what we do is we apply now our network. So we ask our network, okay, here is what is being recorded. Tell us if there is an event, if there's a possibility of an event here. And we ask all these 5 stations, and we select a window to be an event if 2 out of the 5 stations say that there is an event, because there still can be some local sources of noise that can. So this is just to add additional robustness to our network. So this is essentially what we do in terms of the methodology of things. Going to the results part now. So this is what we get. So in this 2-month period, our network tells us that there are 45 events, and we go back and verify those. And 40 of them are true, and 5 we are not sure about because they are kind of in between, and therefore we tend to say that, okay, we're not sure, so probably these are false alarms. And more importantly, if you remember, we were training using the cataloged events, right? And therefore we had, in this 2-month period, there were 23 events already in the catalog. And our network was able to find 20 out of those 23. And the reason why it does not find all of the 23 is because some of the events, as you could see here with these yellow dots, are happening outside of the Zeerijp region. And some of them have very low magnitude. So therefore, they appear very noisy on these 5 stations. And therefore, the CNN algorithm is not able to detect them as events, likely events. In comparison, we use a popular technique that has been around, I think, since the 70s, called short-term average, long-term average, STLTA. It was able to pick 20 events in the same time frame, but it gave 149 false alarms. Now, those of you who are expert in this know that you can tune the STLTA parameters to really increase the number of events that you have, that you can get, but then it would also mean that you would also increase the probability of getting more false alarms, or vice versa. You want to reduce false alarms, you would pick less events as well. And STLTA was able to pick only 10 out of those 23 cataloged events. So therefore, this shows us that even though those events were kind of quite good because they were detected by KNMI, but STLT was struggling with identifying most of them because, of course, some of them were very noisy. And then we also use a technique called template matching. And what template matching does is it takes some master event. So it takes some big event that happened in the region, and it takes it as a master, and it does cross correlation with the waveform of what your seismogram is recording, right? And therefore, if you have a high value of correlation, it means that this is likely an event. Now, the good thing is that template matching can bring out events from noise because of this correlation property. But the bad thing is that it is highly dependent on the master waveform. And therefore, if you have a different kind of event, different mechanism generating a different kind of event, it's highly likely that template matching will miss that event. So this is what we see. So essentially, this was done by our collaborators at Seismic, and what they did was they used all the 23 catalog events as their masters, and they were able to select, or they were able to pick 11 events outside of the catalog. So as you could see, we were able to identify around 25 events outside of the catalogs. They were able to get, 20 events outside of the catalog, so which is like 100% increase in terms of the number of events that we found, whereas Seismic was able to get only 11 events through their template matching algorithm. But there is another interesting thing that it was able to pick 2 additional events compared to our convolutional neural network, which we missed. But it also missed several events. And the reason is, again, it goes to the point that it's able to bring out events from noise, but it is highly dependent on this master waveform. And therefore, I think there's a good synergy between these two algorithms, because the way we train our neural network, or the way we collect data, is we only rely on data that we can visually see as an event. And therefore, if it's highly noisy, if it's kind of buried under noise, then we throw it away. And therefore, our network is not trained for that. So therefore, one good possibility is to combine template matching with convolutional neural network, in the sense that you use template matching to detect a lot of these noisy events, and then throw them into the mix of training and improve your accuracy. All right, just to summarize, what we discussed in this part of the talk is that we have developed a reliable approach to detect low magnitude events while minimizing false alarms, which is an important consideration, of course. And the novelty of this work is that we designed something that is in particularly valuable for wherever there are these multi-level sensor networks. All right, if you are interested in knowing more about this, you could see our talk at the SCG AI workshop, which was supposed to be held in Oman, but now it's fully virtual event in November. And also, I'll be talking about the same problem with a different take at the EAG annual meeting, which is in December. All right. So this was all about detecting earthquakes, and now we're going to talk about locating them using an artificial neural networks. And again, I would like to acknowledge my contributors, Chi Hao from CIPR, and we have Mustafa, who's a graduate student. And again, we have help from Seismic, Leo Eisner and his group there. All right, so here is an image on your right where you see this kind of hockey stick pattern, which shows the number of earthquakes greater than magnitude 3 that have happened over the years. And you see this hockey stick pattern is because of the induced seismicity. There is a huge nuisance in a lot of areas, particularly Oklahoma. And therefore, detecting those earthquakes and also locating them is very important to see those fracture patterns. And therefore, increasing use of hydraulic fracturing and wastewater injection will need us to develop mechanisms where we can do this task in real time. That is, we can detect them in real time, and we can locate them in real time. And therefore, there have been people working on this technology using convolutional neural networks to detect such small magnitude earthquakes in real time. However, what they do is they rely, again, it needs training, therefore they rely on historical data. So for example, if they're trying to, for example, this study by Perol et al., they used a single station in Oklahoma, and they used some data from previous, I don't know, couple of years to train their model. But what if you're going to develop a passive seismic monitoring network and you don't have that historical data available? Of course, you're not going to wait for ages or a couple of years to collect data and then develop this real-time system. And therefore, this is where we are trying to develop a solution. And what we do is Essentially, we propose a solution based on training on the synthetics and applying in the real time. So let's see how it works. Okay, so this is the first thing we did was to do a synthetic study in 2D. So what you see here, top left is a velocity, 2D velocity model, and this black box indicates a zone of seismicity. So we expect our seismicity to be, or events to be located in this region, and we have our monitoring network on the surface at 0 depth. So essentially what we do is we generate synthetic data from events occurring here in this region. We collect or we calculate the travel times on the surface. We try to feed them as inputs to the neural network and tell the neural network, okay, if you see a travel time pattern like this, this is the location. So essentially this is what we are trying to do. And then we test it by feeding some random locations. So we fire some from some random locations within this zone, and we add some noise, so it looks something like this. And then we ask our network, okay, what do you think? If you see something like this, where is the location? And here are the results summarized using histograms. So here's what you see are errors in the x coordinate, and below you see errors in the z coordinate. So what we see is remarkably good accuracy because we have a standard deviation of the error about 14 meters, which is pretty good. And therefore, although this was a synthetic study, we wanted to gain more confidence, and therefore what we did next was to apply it on a real data from Woodford gas shale reservoir in Oklahoma. So what you see here in the background with colors is a velocity model. On top, you see this monitoring network in the star formation, and we have these production wells. And so there are some events in the region, and what we are trying to do is we are trying to see if we can locate them better than other conventional techniques. So here are the results. So what you see here is the difference between our neural network-based approach and a popular conventional algorithm called differential stacking. So what we see is typical that we see very low errors or less differences in the easting and northing directions. These are much less, these are of the order of around, I think, less than 100 meters at most. But we see larger differences in depth. And therefore, since this is real data, it's hard to know exactly what is the answer, but we look at the predictions in terms of depth. So here's what you see along the x-axis is easting, and along the y-axis you see depth. And in red squares you see the prediction by neural network, and in black circles you see the prediction by diffraction stacking. What we see here is that neural networks give us a solution that has much less variation in depth, which is more reliable and more trustable than the solution of diffraction stacking, which has a lot of variation in depth. So therefore, it's well known that the depth trades off with the origin time, and therefore this depth issue, this is an issue, but we always want a solution in which we have this minimum variation in depth. So this is just a quick summary of what I just outlined. It's a novel approach to locate earthquakes in real time. So once you have trained this, so the training process takes time, of course, but this is done offline because we have synthetic data. And then once you are ready to deploy it, it's able to detect events in real time. It is a matter of, I think, microseconds, milliseconds to do this whole process, just a single evaluation of the neural network. And of course, if you want to achieve full automation, you have to cascade it into a network where you have, first, you want to detect those events, which means, the first problem that I was talking to you about, detect those events. The next is picking those travel times. And the third is to locate those events. So if you have this cascade, they can work together, and they can give you solutions in real time. However, there are a few challenges that should be outlined here. One is in real data, you may have missing data, right, in real cases, which means that maybe there is a particular station that is not properly installed, or there is some human activity going on, therefore the station is noisy and you cannot pick a travel time on that. So therefore, what we do in this approach is, of course, we have some missing data and we use something called Kriging-based interpolation. But now we are developing another method for that, in which we avoid some of this, because interpolation, after all, may introduce some errors, and therefore we're trying to develop a method that does not require this interpolation step. So this is something in development. And there is another issue of unknown velocity model. Now this is an inherent limitation, and one I would say maybe like a chicken and an egg problem. Therefore, you can have an active seismic survey before, or you can have some kind of other ways of getting the velocity model, which is something that you should know for this method to work. Yeah. So this is all about this thing. If you want to know more if you want to know more about this problem, then you could attend the talk at the EAG annual meeting and also at the SEG AI workshops. All right. So this brings me to the last problem that I'm going to define in detail. And this is a personal favorite on solving partial differential equations using physics-informed neural networks. So far we have seen, I may have mentioned these terms, feed-forward neural network, convolutional neural networks, and now I'm bringing in a new term, physics-informed neural networks. And this is in collaboration with Ehsan Haqiqat at MIT, of course, through our partnership with MIT through Rubin. And Ehsan is a postdoc with Rubin, and this is also a strong partnership with KAUST, with my advisor, former PhD advisor, Tariq Al-Khalifa, and his student, Chao Song. And we're working on several different equations, not only the eikonal equations. All right. So the eikonal equation is not only used in seismology, it's used in many different areas. It's used in robotics for path planning, it's used in computer graphics, it's used in semiconductor manufacturing, therefore it's an important problem. In seismology, the eikonal equation regulates seismic wave travel time. So if you have an earthquake, for example, here, the time it takes for it to reach the surface or a station over here, that you can model using eikonal equation. Now, the conventional techniques that solve eikonal equation are usually ray tracing or something called fast marching or fast sweeping. But one of the problem with these techniques is that there is no information transfer from one simulation to the other. And what do I mean by that is, if you have an earthquake and you do a simulation, for a new earthquake, you have to do this simulation entirely, and there is no information that you can carry from your previous simulation into the next one. You have to do the same amount of computational effort. So we look into the machine learning literature if we can do better than this. And therefore, at this point, I would like to highlight one thing before we understand how physics-informed neural networks work, is what does a loss function or a cost function do in neural networks? So previously, when I was telling you about face recognition using neural networks, what it does is it takes the image of a cat, for example, it does the calculations at the output, for example, it says dog. And we say, no, 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 you don't have to say that. This is not a dog, this is a cat. So what it does is it subtracts the difference between its prediction and our label or the thing that we supplied, and we propagate it back to calculate the solution. And this subtraction, this is embedded in something called a loss function. Now, in physics-informed neural network, we are going to play with the loss function a little bit, and this is the trick here. So this is what I'm going to say. So this example that you see here, for example, if you're supplying a network with a 3, you're trying to distinguish between different handwritten digits. It says something like this, which is kind of a mixed bag. And you say, no, 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 I don't want different answers. I want one answer, which is a peak at 3 and 0 on others. And therefore, this is used to inform the network and to improve the network. Okay. So here we're talking about physics-informed neural networks. Oh. All right. So what we do here is we play with the loss function. So the loss function is kind of used here to apply this equation. So what we want to do is to solve this partial differential equation. Therefore, we can play with the loss function. Therefore, we don't want all the solutions possible. We want solutions that minimize the residual of this PDE. So this is residual of a PDE from the eikonal equation, and therefore the unknown here is tau. So we want only taus that minimize this residual. We don't want any kind of tau. And therefore we embed this in our loss function, but we also want something else. We want our taus to be positive. So there's a term that forces the solution to be positive. And there's something else we want. We want our tau at the source location to be 1. And this is because I'm using a special variation of eikonal equation, which is called factorization. And therefore, the final solution that you obtain is by multiplying this physics-informed neural network-based solution or the neural network-derived solution, tau, with T0, and this gives us the travel time. So if this is too complicated, in terms of the equations, let us try to understand this in terms of a flowchart. So essentially, what is the process? We first feed, so you have this computational domain, right? I don't know, whatever it is, 0 to 10 kilometers along X, 0 to 20 kilometers in Z. You take some randomly located points, X star and Z star, you feed them to your randomly initialized neural network. what is going to be the output of this randomly initialized neural network? Just garbage, because it has not been trained. It doesn't know what to output, right? And now we start this teaching process or this minimization process. And therefore we have some additional inputs to it, which is the velocity and these known travel time factors. And therefore taking these into account, putting them into the loss function, it tries to give us a solution, or it tries to, play with the weights. Again, these weights are coming back. So play with the weights to make sure that the solution minimizes our loss function. And once we have a trained neural network, we feed all the points in our computational domain, and we get this tau hat, which is an approximation, of course, of the solution, and we multiply with T0 to get our final travel time solution, which we hope is as accurate as possible to the correct solution. And therefore, this is the outline here. Now, some of you who are used to supervised learning problems may be really confused here. So where did you supply the data? So where is the data going in to teach the neural network? So this is something that needs to be clear, because this is not an example of supervised learning. This is a different problem. This is a different way of using neural networks. In this, essentially what we are saying is that, I'm not going to supply any solution, but what I'm providing you is this loss function based on the PD. Therefore, please go back, update the weights until you're able to minimize this loss function. So therefore, there is no training set here. Therefore, there's no labeling here that you need, like we needed for our previous example. So therefore, there is no stage of data collection or anything like that. So now let's move on to see some numerical tests of our solver. All right. So this slide just details a bit about our neural network. So we use a neural network with 10 hidden layers and 20 neurons in each layer. The activation function, which I haven't talked about yet. So activation function is a way to add nonlinearity to the neural network, which is essentially how you make neural networks learn nonlinear features. And therefore we have this arc tangent activation function for all the hidden layers, and the final layer is linear because we want the output to not be restricted, which is the case with arc tangent. The optimizer is Adam with a particular learning rate shown here. All right, so I'm going to show you first some solutions that we get from our physics-informed neural network. On the left, you see a 2 kilometer by 2 kilometer model. What you see in the center is source indicated with black star. And this is a model that kind of tries to replicate a smoothly varying Earth with increasing velocity as we go deep. And here is the solution. This is not the solution. This is the error using a conventional technique called fast marching. And this is typical of fast marching, that we have large errors in the diagonal direction. So this is well known. Whereas this is the solution from physics-informed neural networks. Now, one thing you would see is just looking at these numbers is that the solution is more accurate, but also it's kind of random. So there is no structure inbuilt to it, and this is because of this stochastic optimization process. So this is good that it's able to compute the solution accurate. But is there anything else we can gain from using this model? The physics-informed neural network. So what we do now is, now that we have trained a neural network to solve that problem of solving an Earth with increasing velocity, we're going to make some changes. So the first thing we do is we relocate our source. So it's not at the center anymore, it's somewhere over there, indicated with a black star. And we also include a horizontal gradient in the velocity. Now, what we try to do is, instead of retraining the neural network from scratch, what we do is the network that we have already trained from the previous step, we are going to use that and try to see if it can help us solve this problem quickly. And this is what happens. As you can see here, we get good accuracy. Again, this is fast marching method. This is physics-informed neural network. The accuracy is pretty good. However, the main thing I want to point out here is this curve. So this is the loss function, how the loss function decreases when you use a randomly initialized neural network versus when you use a pre-trained, so the one that was trained before. Even though we change the velocity model, we change the source location, still we are able to converge pretty quickly in about 25% of the cost. And with further optimization, we can even reduce it. But this just to explain the point of what's happening. Moreover, we could go one step further. And what we can do is we can calculate solutions using several different sources in the model. So for example, you have this model, a vertical varying model, and you compute solution using these 16 sources. Now, for problems like seismic inversion, when you want to locate earthquakes, or when you want to invert for velocity, you may have to do it for thousands of sources. And therefore, what we are saying here is that, okay, if you are able to compute solution for 16 sources that are equally spread in the domain, then we can also add the source location as an input, and we can train our neural network to see this relationship that when this is the source location, this is how the travel time field looks like, and therefore we are trying to now predict solutions for all the other sources using this neural network. So what this does is, this means that we don't need any training, we just need a single evaluation. And this means this is very similar to getting to an analytical expression for solving a problem. So those of you who are into computational field would know that, how simple it is to solve when you have an analytical expression versus doing it numerically. And therefore, this is essentially what we try here. We pick, after training, we pick a randomly located source, and we compare its solution with the fast merging method. And this solution is computed instantaneously. I think it took us about 0.1 of a second on P100 GPU to compute the solution. So this is really instantaneous because this could massively speed up our computational capabilities. And just to show you here that this is not only true for simple models, we can also try complicated model like this part of the Marmousi model. Again, we get a good solution. However, we observe much slower convergence here. So it takes a lot of time for the network to converge to the solution. And I think this is one of the challenges that we need to address in order to further advance this work with physics-informed neural networks. So just to summarize what we have just seen, it allows, this framework allows us computational speed up using transfer learning and surrogate modeling, as I showed. It is a mesh-free method. So while we were training, we used randomly located points, and therefore this does not require a regular mesh as finite difference approaches. Therefore, it can handle topography very easily. Sources and receivers do not have to be on a regular grid, which is often a problem with those conventional techniques. Moreover, I think one of the key points as a programmer would be the ease of deployment on computations across a variety of platforms. So if you want to use networks, if you want to use other algorithms on CPUs or GPUs, you have to write separate codes. If you want to use clusters, you have to write separate codes. The great thing is that because we have TensorFlow at the back end, you can take the same script, whether you want to run it on a CPU or a GPU, you don't have to change anything. However, there are a few challenges that I outlined here, which is the problem of sharp velocity variations, and this is something we are actively working on. And the other problem is parameter tuning. So you see, neural networks have a lot of parameters, a lot of choices to make. So this can be a problem, this can take a lot of time, and therefore this is another challenge that I think needs to be addressed in the future. And this is, of course, in general true for all neural network related problems. For more problems, I think you could refer to our talks at the upcoming SEG annual meeting, in which I have a talk, and Tariq Al Khalifa from KAUST is also talking on something we worked on, the Helmholtz equation for solving for the wave fields. And also we have talks at the EAG meeting, and we have some preprints already available that you can read on archive if you are interested in getting more details. Now I'm going to just quickly outline a couple of topics that are very collaborative. So this is deep learning in digital rock physics. And the guy you are seeing here is Gunter, believe it or not. I believe it will be very hard for you to recognize Gunter when he was so young. Yeah, Gunter could testify if it really is his picture or not. But what we are trying to do here is that we are trying to use convolutional neural networks to extract rock parameters. There's a long project, and we're trying to extract rock parameters digitally or automatically using convolutional neural networks. So very quickly, I'm just going to highlight what we are trying to do is we take this low exposure CT image that you see here, very noisy, very hard to see, and we feed it at the input, and we take this high exposure image and we feed it at the output. So Gunter has run these tests where he kind of collects these images with low exposure time and high exposure time, and therefore we train a neural network to take this kind of image in the future and give us something like this. But what a neural network does is also a surprise to us, is that it gives us something like this, which it is able to even remove the noise that was in the high exposure image. So it gives us something very close to the true data. Now this was a synthetic test I'm showing to you, but it gives us really good results. And this is excellent, because the accuracy of properties that we want to get from CT data is highly correlated with the image quality. And therefore, this is a very important step that we are doing. And also, I think it's very important that in the future, that why having these low exposure images help is they allow us, an increase in temporal resolution, which is important for phenomena like flooding, and you are kind of want to see how things evolve as you're flooding the rock. All right, so what we do here is we study different factors, number of training images needed, we study different loss functions, applicability of transfer learning. All of these I leave it to Gunter. I think at some point he will be able to show us in one of these CIPR meetings what he's doing and share with all of us the progress on this side. Now I'm going to show one more thing for our geology friends. There is so much opportunity to do in geology, I believe. As an outsider, I see geology is a place where I think it can benefit so much from deep learning, because a lot of the things that geologists do require a visual inspection and analysis, and convolutional neural networks are really smart at doing that. And this is a collaboration with Korhan, and this collaboration started right in front of one of our elevators, where I was trying to sell deep learning to Korhan, and thankfully he found value in deep learning, and now we are doing some very interesting things, which I would leave to Korhan to share in detail. But here are a few ideas, that where deep learning could help geologists in fossil analysis, core description, etc. So I think geologists spend a lot of time after they collect data in doing these kind of analyses, and therefore all of this could be automated. And therefore, while it takes a geologist, I don't know, 30, 40 years to get trained and be good at, at his art, it would take much less to teach the same thing to a convolutional neural networks, and the results, of course, would not vary depending on the mood and the time of the day, for example. All right, so by now, I hope I have conveyed to you that deep learning has a lot of potential in the area of generally geosciences, but there are some limitations also. So let's look at the flip side of it very quickly. And the first thing I want to illustrate is the limitation in adversarial setting. So what do I mean by adversarial setting is when you have, for example, researchers have shown that, this is a stop sign that is very clear to all of us. Now, this is also a stop sign, but just contains these white and black patches. However, researchers have shown that by just adding these black and white patches, they could fool the network to identify this as a speed limit 45 signal, so which can have catastrophic consequences. Moreover, researchers have shown that you could take an image and add a particular kind of noise to make it look like another image. So here what they did was to take an image of a sloth and add some kind of noise to it, which of course we cannot see with human eyes because it's very low. But to a convolutional neural network, it looks like a racing car because they have added this noise based on this image. And therefore the network thinks that this is a racing car, which is totally absurd, right? So this is one limitation which keeps deep learning researchers awake at night. Another thing is opacity. So here what you see is interpretability of an algorithm versus complexity. These are some machine learning algorithms that are simple, less accurate, but more interpretable. So you can guess when an answer is wrong, what is the reason somehow, or you can gauge, why is the network not working as I expected. Whereas deep neural networks, they are complex, they can do great things, but when they fail, it's hard to know why they fail. And therefore this can have really big consequences. If you are trying to have a self-driving car, you don't know when it fails, why it failed. If you're talking about medical diagnosis system, if it gives wrong diagnosis, it failed, why did it fail? So these are real challenges. However, so now trying to conclude everything that I showed to you guys, I believe there is a huge potential that remains to be tapped in geophysical exploration, in particular in geosciences in general, of course. And I believe we just started this journey. There's a lot more to go. We need a lot of capable people to join us and do this kind of work and advance the science. One of the problem with deep learning method that researchers identify is that it needs several hundreds or thousands of images to be trained, right? So for example, if you want to teach a network to learn to identify a cow, it takes, for example, 10,000 examples of cows, right? Different angles, different ways. But it took only a few examples for my 3-year-old daughter, like a few, 5 or 10, to identify cows in different scenarios, because humans never start with a blank slate. They have information because they have seen maybe a lion somewhere. They identify that this is how an animal looks like, and therefore this is a different animal. Therefore, there are a lot of similar features as well. And therefore, transfer learning is something that allows us to learn quickly. And there are new technologies coming like graph networks, deep reinforcement learning, that are trying to address some of the limitations that I mentioned to you towards the end of my talk. Deep reinforcement learning is actually about mimicking how humans really learn. So we don't normally learn when people tell us something. Sometimes we just go, experience the environment, and learn things on our own. And this is what deep reinforcement learning is doing. It has shown great success in gaming AI. If you may have heard of, a deep reinforcement learning based network beating the Go champion in 2016. And since then, no human has been able to beat this kind of network because they have advanced in capabilities. Now, fundamental progress in deep learning may not be easy or fast, but we are not at a dead end, of course. So there is a lot of hope, and I want you guys to see this not as a problem, but as a challenge where we could, contribute to improve things. Finally, I would like to again acknowledge my contributors to this work. Thanks to our college and their support, that we have these partnerships like with MIT and Seismic that allow us to work with the best in the business. And I would like to finally mention a special thanks to our chairman, Dr. Abdul Latif, and mainly because I know that he spends a lot of effort in making sure that the faculty gets as much time as possible for research. And this is something I really appreciate and admire. So I thought I should say it in public as well. And I would also like to thank our dean, Dr. Kabi, for his support to research and for all the operations in the college. So essentially, this is all I had. I would leave you. And I would like to also thank you, of course, for your attention. I would leave you with this conversation between AI and a human, so that it shows that deep learning models are not only good on science and engineering problems, but also they are creative, and their capabilities would increase as time progresses. So thank you, everyone, for listening in. I would be very happy to answer any questions that you may have. Thank you very much. I took much more time than I expected. So
do you have any questions?
If there are questions, I would be happy.
Yeah, no, I'm checking. I'm perusing the list of participants.
We have Sharif.
Okay, Sharif, yeah.
Well, thanks, Amir, for a very nice presentation and idea about your current research in machine learning. I have a question about the second application.
Mm-hmm.
Well, I was expecting that you will not have the velocity model, but I did not expect that you don't have any information about the velocity. Well, the slide 21, I think, yeah, I can see it here. Slide 21 shows that you have just a simple layered model that you used for creating your synthetic data. Do you think this is enough to get good results? Is it better if you have some knowledge about the actual velocity model? Will it improve the results? Can you just elaborate on this point again, please?
Yeah, so the method is, of course, dependent on the velocity model. And if you think about it, I mean, this is a inherent limitation with the method, of course, that it relies on the velocity models to generate the training data, right? So therefore, if you have misspecifications in your velocity model, that may be a problem to study how much that would affect your final accuracy, of course. But here we are assuming that we know the velocity model, of course, because if you look at other techniques that rely on, for example, convolutional neural network, when they are using their, when they are training their network with historical data, of course, that historical data is generated, or those historical locations are generated using a particular velocity model, and therefore a velocity model is embedded in it. Therefore, maybe one way to handle this would be to have some kind of a Bayesian way of thinking about it, where you not only have a single velocity model, but a probability distribution, and you train your network based on several different velocity models, so it can generalize better to the real scenario. So that would be my thought. I don't know if I answered your question.
Yeah, you did. But Do you have any other limitations like the, well, you don't know the velocity, that's okay, but do you have any other things like the source need to be within this range of depth? Any other limitations to?
Yeah, I don't think, because in the training, you can have your sources within the entire model. Now on training, you can spend all the time you want, but just to be efficient, you would want to train on locations where you expect your real events to lie. And therefore, this is the thing. So I cannot think of other limitations other than what I mentioned. Of course, some of the limitations are inherent, and this is with any other method that is doing locations.
Okay, thank you, Omer.
Thank you.
There is one more question from Dr. Farati.
Oh, thank you. Very interesting talk. I want to refer to the physically informed neural network you use for solving that model.
Mm-hmm.
Yeah. So for the loss function,
mm-hmm.
You are not also matching any data there?
No data here. If you want to just look at here, there is no data used in training. It's purely based on the loss function. So essentially what happens is, if you feed some coordinate location, it gives you some garbage, but eventually it will learn to give you the correct solution through this loss function.
Okay, also do you learn the parameters in the equation, or you assume them?
It is possible to learn the parameters. Right now, this is a forward modeling problem. So we believe we know that, but definitely learning parameters is definitely possible, yeah.
So here in this neural network, you're just learning the solution, basically, or solving the equation.
Right. But simultaneously, you could train it to learn also this velocity parameter. And this is something I'm working on.
Yeah, exactly. So this is what is you. For such, but if you have data also, can you build this into the loss function?
Exactly, yeah. So for example, something like this, right? So we know that the travel time at the source has to have a certain value, right? We don't know at other locations, but now when you know them, of course, it helps the network to converge faster, and because it's not starting from random, but it has some solution at some points to constrain the solution space. Definitely, it will help.
Just one final one. Did you compare, so you use physically informed neural network. What about other architectures? Did you?
Okay.
So other architectures?
Yeah, so the name physics-informed neural network does not mean it is a different kind of architecture. It is a feed-forward neural network with physics to inform the solution. That's just the meaning of it. So it's a feed-forward neural network, but definitely you could use more advanced networks. And I've seen one example where they're using ResNets. And I don't know, I haven't tried myself, but I think it's possible.
Thank you.
Thank you very much.
Okay, Omer, thank you so much for kicking off our new series, and very much looking forward to seeing everyone next week.
Thank you, John, for the claps. All right, thank you, Gunter. Thanks for inviting. Thanks for everyone. Yeah. If you have questions, you can feel free to contact me on my KFUPM ID email. So I'll be very happy to answer any other questions or any collaborative opportunities as well. Thank you, everyone. Send me to just.